rubber balls that I'm going to roll down the ramp behind me and let the balls collide with the wooden block at the end of the ramp. The balls have very nearly the same mass, but very different elasticities. So when I drop the two balls, you'll see they bounce differently. Okay? Okay, so this ball is very bouncy, high elasticity. This ball, not very bouncy, low elasticity. So let's roll the balls down the ramp and see what happens when they collide with the wooden block at the end of the ramp. So first, the not bouncy ball, we'll roll it now. It collides with the wooden block and makes it shake around, but the block stays where it was after colliding. Now the bouncy ball, we'll roll it down the ramp and see what happens when it collides with the wooden block. Here it comes. So what is it about those two collisions that causes a different thing to happen to the wooden block?
So for collisions, there's many different ways to describe those between objects. In any collision, the total amount of momentum is conserved, but generally the total kinetic energy is not conserved. What that means is that it will have the same amount of momentum before the collision as it does afterwards. So we're going to talk about perfectly inelastic collisions, and these are when two objects collide and move together as one mass. It's called a perfectly inelastic. So basically, if they collide and stick together, since the two objects stick together and move as one, they have the same final velocity. So we're taking that law of conservation of momentum equation and just altering it slightly to show that the two masses stick together on the right side of the equation. So we add them together and they only have one velocity because they act as one object. Kinetic energy is not conserved in perfectly inelastic collisions. So if we look at the sample problem, an 85 kilogram fisherman jumps from a dock into a 135 kilogram rowboat at rest on the west side of the dock. If the velocity of the fisherman is 4.3 meters per second to the west as he leaves the dock, what is the final velocity of the fisherman and the boat? So you can see in this situation they're kind of sticking together because he is going to be in the boat. Okay, so what we know is the mass of the first object, which is going to be the fisherman, is 85 kilograms. The mass of the second object, which is going to be the rowboat, is 135 kilograms. The velocity of the rowboat initially was 0. It was at rest, and the velocity of the fisherman initially was negative 4.30. We're making it negative because it's west, and we know that it's perfectly inelastic collision because they stick together and move as one at the end. So here's our inelastic equation. So the next step is to plug in our numbers. So we have our fisherman is 85 and he's moving at negative 4.3, plus our boat was 135 and that was at rest, so that's 0. In the end, we add the fisherman and the boat's mass together and we're going to look for that final velocity. So now we just have to do the math. I'm going to multiply the 85 and the negative 4.3, and that gives me negative 365.5. The 135 times 0 gives me 0, so that's going to go away. And the 85 plus 135 gives me 220, and I'm still looking for that final velocity. So the next thing I'm going to do, the 0 goes away, so I just need to divide both sides by 220, and that gives me negative 1.66 meters per second. And what that negative tells me is that they're moving at 1.66 meters per second to the west. If we look at the change in kinetic energy for this problem, the initial kinetic energy of the boat was 0 because it wasn't moving. The initial kinetic energy of the fisherman We know kinetic energy is 1/2 mv squared, so we're just going to plug in 85, and the velocity is 4.3. We can put the negative there, but it's going to go away because we're going to square that number. We want to square the number first, so we get 1/2 times 85 times 18.49. I'm going to multiply all of those together, and I get 785.8 joules for his initial kinetic energy. So the total initial is 785.8. I'll just add those two together to get the final. I'm going to do 1/2 mv squared still. My mass now is going to reflect that the fisherman and the boat are together. So I'm going to add those two together, and I'm going to use the velocity that I just found of 1.66. So I'm going to square that first, and I get 1/2 times 220 times 2.76. And that's going to give me 303.1, and that's the final. So you can see from the initial to the final we've lost some. And the amount we've lost, we just subtract, is 482.7 joules.